Hello students, in this video we are going to learn about the properties, valency and atomic size and their trend in the periodic table. An atom is said to be stable only if it follows Duplet or octet rule. Duplet rule states that if an atom has K shell as its valence shell and if it has 2 electrons, it is stable. Here, hydrogen as well as helium has K shell as its valence shell, but hydrogen has only 1 electron while helium has 2 electrons. Therefore, hydrogen is unstable and helium is stable. According to the octet rule, if an atom has valence shell other than K shell, it should have 8 electrons in order to become stable. In this case, oxygen has only 6 electrons in its outermost shell, whereas neon has 8 electrons in its valence shell. Therefore, neon is stable, whereas oxygen is not. So, what will these atoms do to attain stability? They will lose, gain, or share electrons to become stable. Let's see the case of sharing first. Here, the two hydrogen atoms have 1 electron each in their valence shell. They need 1 more electron to become stable. They will share their electrons and become a molecule. Since the number of electrons shared here is 1, they have the valency 1. Now let's take the case of hydrogen and chlorine. Hydrogen has 1 electron in its outermost shell and chlorine needs 1 more electron to become stable. In this case, hydrogen will lose its electron and chlorine will gain this electron to attain stability. They will become a molecule, hydrogen chloride, in which hydrogen remains as a positive ion while chlorine remains as a negative ion. Here, hydrogen lost 1 electron and chlorine gained 1 electron. Since the electrons lost or gained is 1, both hydrogen as well as chlorine will have the valency 1. So, valency is the number of electrons gained, lost, or shared by an atom to attain stability. It mainly depends upon electronic configuration. Down a group, the electronic configuration of the elements is similar. The number of valence electrons remain the same down a group. Therefore, the valency is also same. For example, the first group will have valency 1, the second have valency 2, 13th group have valency 3, the noble gases have valency 0 as they do not take part in chemical reaction, and so on. Across a period, the electronic configuration differs and therefore the valency varies. Now let's have a look at the next property, atomic size. Atomic size is determined by the atomic radius, which is the distance from the nucleus to the valence shell. The atomic radius is in nanometer. It is very small and cannot be seen even with powerful microscopes. But with the help of scanning tunneling microscope, which was developed in 1980s, imaging at atomic level is now possible. There are two factors which decide the atomic size: number of shells and nuclear charge. Down a group, the number of shells increases. For example, lithium has 2 shells while sodium has 3 shells. As the number of shells increases, the distance from the nucleus to the valence shell also increases, which means the atomic size will increase down a group. Across a period, the number of shells are the same. Hence, the deciding factor here is the nuclear charge. In case of lithium, there are 3 protons and 3 electrons, whereas in case of boron, there are 5 protons and 5 electrons. And hence, the nuclear force of attraction in case of boron is much higher than that of the lithium. As the nuclear charge increases, the distance from the nucleus to the valence shell will decrease due to the force of attraction, and therefore the size of lithium is slightly more than the size of boron. That is, across a period, the atomic size decreases. To summarize, atomic size is determined by the atomic radius, which is the distance from the nucleus to the valence shell. Down a groove, atomic radius increases, while across a period, atomic radius decreases. That's all for now. In our next video, we will learn about metallic and non-metallic properties and how they vary in the periodic table. Thank you for watching. If you like the video, please do like, share and subscribe. Bye bye.